So welcome to lecture 14 of the course. So today we will change gears. We've been looking at dark matter in the last lecture. Today we will switch to a little bit of how we can measure the distribution of dark matter within the universe. And a powerful technique for doing that is gravitational lensing. Okay. The bending of light is similar to deflection of massive particles, except that GR predicts for photons the bending to be exactly twice the Newtonian value. And it's given the amount of bending alpha is given, depends on what the mass of the body that's doing the bending is. And it also depends on the impact parameter, which means the photon that's coming from behind, what is the distance at which it is the closest distance it reaches from your lensing body. So you can write it like this: 4gm over bc square, which is equivalent to 2 times the Schwarzschild radius divided by the impact parameter. This formula is only valid if b is much greater than rs, which usually is the case. So for example, for the sun, the deflection angle alpha is about 2 arc seconds for stars that are very close to the solar limb. Of course, B is much greater than RS in that situation. The thing to remember is that these deviations are quite small. Even for the sun is 2 arc second. And you people must know of the experiment that was done in 1919 during the 1919 solar eclipse to measure this deviation and to test whether it matched the predictions of Einstein's general theory of relativity. And it turned out that it matched, and then after that Einstein became instantly famous. But newer analysis of that data set has revealed that they made a lot of errors in measuring the deviation. And so actually they didn't find confirmation of Einstein's theory at all, although it came in the newspaper the next day. So really, now we can of course do better and confirm that. So it's not that Einstein's theory is wrong, Einstein's theory is correct, but the measurement that was done in 1919 was full of many errors. But we can use this principle for studies of galaxies. So suppose you have a galaxy which is here. This acts as the lens. And you have, let's say, a point source exactly behind the galaxy, and you're observing from Earth. So what happens is the light rays that come from that point source get lensed, they get bent, and they reach the Earth from 2 different or many different directions. So if the situation is completely symmetric, then what happens is you see the Einstein ring. Okay, so this is what you see over here. This is known as the Einstein ring. So there is a single point source exactly behind the galaxy, which produces this ring. Now, so here you have a slightly different situation. Again, you have a point source, but it is not perfectly lined up behind the galaxy. And in that situation, if you're observing it from Earth, you don't see a full ring, but you may see multiple images of the lensed object. These may be 2 images, 3 images, 4 images, and so on. So this is the basic idea. This particular kind of lensing, okay. So one way of measuring it is to take the spectrum. Okay, if you take the spectrum, if it is the same object, okay, the amount of redshift that you will see in that spectrum will be similar, or identical, and you will also see the spectral lines and their relative line strengths, etc., to be the same. So that is how you can distinguish. Yes. So these the geometry is such that if you're lensing with a galaxy, you must have, of course, I mean, you won't be lensing star generally, although a lens star was found by Hubble a few days ago. I should have included that maybe in the next lecture. I'll show that picture. So if it's a galaxy which is being lensed from the background, then all of the things that I just said all hold good. You can't do it. But interestingly, I remembered one thing that about 20 years ago when I was doing my PhD, 25 years ago when I was doing my PhD, we found a pair of quasars which were very close to each other on the sky. And they had the same redshift. And they had very similar spectra. So the debate was, are these really physically close by quasars, or are they lensed images of the same object? Now, yeah. Sometimes the lens can be quite faint and invisible. Okay, so you don't really know. What was going against these being lensed objects was the fact that the separation was rather large. I mean, the angular separation. So which meant that there were very few geometries, lensing geometries, that give you such a large separation. But there was some conclusive evidence that we found. I'll mention this later because I haven't mentioned how we found conclusive evidence to definitively prove that these were two separate quasars. They were not lensed images of the same object. So we'll come to that a bit later. Yeah. So this kind of lensing, where the amount of bending is quite large, macroscopic, and can be directly measured, typically of the order of arc seconds, is called as strong lensing. But there is a much more common form of lensing known as weak lensing, which we will come to later. But let's talk about strong lensing. So if you ask the question, what does lensing tell us? That photons and kinematic modeling, virial theorem, etc., don't already tell us. Okay, because we are using photons to map the baryons in the universe, no problem with that. And we are using either kinematic modeling, or like the rotation curves of spiral galaxies, or the virial theorem in virialized systems, to measure things like the total dynamical mass of galaxies and so on. So what will lensing tell you that we don't already know from these kind of studies? So what are the things you can learn? Yeah. So
the content, how much lensing it is.
Yes.
From there we can how much mass.
Yes. Yes, that's correct. Okay. And so you can definitely measure dark matter. Correct, correct. Correct, correct. So right. So the first answer, of course, if photons only doesn't tell you much, it doesn't allow you to measure dark matter. But the probing the dark matter, we always make additional assumptions. Like one, there are baryons, and we need with lensing, there is no need for knowledge of orbits. Okay, is it a spiral galaxy? Is the velocity field rotational? What is the maximum velocity? Okay, etc., etc. Or stars going around the supermassive black hole, you have to measure each velocity of each star and so on. Or if you're looking at virialized system, you have to make the assumption, or you have to verify in some way that the system is virialized and so on, to convert the velocities or the velocity dispersions into masses. With lensing, no, it's a sort of assumption-free thing, right? Just use pure geometry to build mass models of the lens. Yeah. The probability of getting two strong lenses is very small, okay? And in most cases where you get strong lensing, you actually see the lens. Maybe a single galaxy, maybe a cluster of galaxies, to see it. So the chance of getting two strong lenses aligned is very small. With weak lensing, what you are saying is perfectly true, that there will be one galaxy which makes a small deviation, another galaxy makes a small deviation, and the whole thing comes to you deviated in many different ways. Okay, deviated several times along the path. That one can use to model things in different slices. I'll come to that when we talk about weak lensing. One powerful manifestation of weak lensing is what is called microlensing. It's a strong lensing phenomenon, but the idea was that some people suggested that maybe the dark matter is not composed of atomic, subatomic particles, but these are big objects which for some reason are not emitting light. Okay, so we know, like for example, there could be brown dwarfs, okay, which unless you observe them with sensitive infrared telescopes, you will not see them. Or they may be Jupiter-like giant planets. If they are just floating around, devoid away from their parent stars, then if there are thousands of Jupiter-like planets all floating around here and there, then they will not emit anything, but they're definitely having mass. So these are referred to as machos, or massive compact halo objects. Halo objects are talked about more, not because there are no such objects in the disk or the bulge, but because in the halo we can actually hope to detect them. Okay. Although these machos, being dark matter, should not be detected themselves, but if they pass in front of a source, for example, a star nearby, they can cause the star to become brighter for some time, okay, days or weeks. This effect has been observed, but detections of the dark matter are not yet conclusive, in the sense that in order to explain all the dark matter that is observed, you need very large numbers of these kind of lensing objects, which means if you're observing stars in the halo, you should see very frequent lensing events. Okay, and there have been a number of studies over the last 30 years or so. The Macho project was one of them. There was another large project called Ogle, and there were several others, where the idea is very simple. You just use a small telescope. Telescope need not be very big. Small means, by modern standards, small, about a 1 meter telescope. And you keep on observing certain fields in the direction corresponding to the stellar halo. And there you hope that some star will get lensed. So you keep on observing, and do that. And this is an example of one event from the Ogle project. By the way, Bohdan Paczynski, the author of this paper, is one of the main drivers of using microlensing to find these macho kind of object. So here's Julian date on the x-axis and the magnitude on the y-axis. And so here it's at about 16.5 magnitude to start with, and it rapidly brightens to brighter by more than a magnitude, and then rapidly fades away. By rapidly, one means on time scales of days or weeks, it gathers. And each black point there is a observation, photometric measurement of the magnitude of the star. Okay. the star that is being lensed. So now there were predictions from various models of how many lensing events you should see. And what was found after many years of research, that the contribution from machos to the entire dark matter budget is very small. Okay, maybe 10%, maybe even less than that, right? And so because of that, now the search for the dark matter particles continues, because we have not yet resolved how dark matter comes. Yeah. Yes, yes. So that's the question. So it can be a variable star also. It is derived from the lensing equations. Okay, so I don't remember what form this is, but it can be derived from a point source being lensed by another point source. Yes, yes. So it's not hard, because these are the simplest objects you can find, right? Mass, single point mass being lensed by a single point mass. You don't have to build any models or sophisticated mass distributions, nothing. And the geometry is very simple, and therefore it's almost like fit to the CMB spectrum, right? It just goes through the data points perfectly, provided your data points have very low error bars. And these are very, very accurate measurements, so it goes through. And numerous such other events have been discovered. Okay. So now the question is, how can we distinguish a microlensing event from a variable star? Okay. So exactly what you asked, that how do we know that this is a lensing event? And yes, it could be periodical. Yes, in this case, it will be a single event. Okay, even if the variable star is aperiodic. Okay, there are some variable stars which just brighten, fade once, and nothing happens for next 1,000 years. Okay, even for such class of objects, they are not going to be fit by the functional form that is predicted for a lensing event. So if you can, if you build a lens model, you will get a perfect fit with the lensing equations, and you won't get a good fit in general with the. So that's what we saw here, right? So what is happening is, normally a photon which is going in this direction would have gone on there. A photon which is coming in this direction would have gone off in this direction. But what is happening, like a convex lens bends light and brings light from a large area to one spot, the same thing can happen in gravitational lensing. It acts like a convex lens and bends the light towards us. And therefore, we see light which we would have not otherwise seen. We see photons that we wouldn't have otherwise seen, and therefore it appears brighter. And the same thing happens with stars in microlensing. Okay. So this is how we distinguish a microlensing event from a variable star. Right. Now you can also have, suppose you have a source star in the background, okay, and you have a planet and a star passing through your line of sight to that distant star. Then what can happen is, you can get separately, depending on the geometry, you can get lensing by the planet, you can get lensing by the star also. Okay, and then you can get, if you plot the magnification as a function of time, as the star moves across, you will see, first of all, multiple images, sometimes 3 images, sometimes 2 images, and so on, and eventually just one image once the system has passed through. And these kind of things have also been found. So we have found a few cases where you have massive, of course, if the planet is very low mass, it won't produce enough lensing. But if you have a widely separated Jupiter or higher mass planet in orbit around the halo star, you will, around this compact halo object, you will see this kind of lensing. So now what? You can't use sun as a lens because it bends it very little, okay, and the contrast is too high, right? I mean, it's like, why don't we observe in daylight, right? You don't observe in daylight, you can't see the stars. So you will, it's very difficult. Only during a solar eclipse does the situation improve somewhat to a level where, that's why that measurement of Einstein's prediction was made during a total solar eclipse. That is why we don't do it with the sun. Okay. Now, over the next decade, this whole microlensing scenario is going to change very dramatically. And it's going to change because of the advent of a new telescope. This is a artist's rendering or a design rendering, but most of the telescope is now ready. The camera is being installed and so on. And by 2024 or so, this big 8-meter class telescope is going to start a survey of the entire sky. Okay, the observatory is called Rubin Observatory, and the survey that it will do is called Large Survey of Space and Time. This is a renaming. Earlier, the Rubin name was not there. Rubin is, of course, named after Vera Rubin, who discovered, who measured spiral rotation curves and discovered dark matter. LSST is used to be called the Large Synoptic Survey Telescope. Now it has been, the survey has been renamed to Large Survey of Space and Time. 10 years of observations. And what will it do? It will do an optical near-infrared survey of about half the sky in 6 optical and near-infrared bands. And it will make measurements of the entire sky based on 1,000 visits over a 10-year period. Okay, so it will gather not just for the halo stars, but in every direction. It will gather 1,000 data points over a 10-year period with different cadences, which means separation in time of ranging from a few seconds to 10 years. The observing strategy is the main about survey, which is called wide, fast, deep survey, will use about 90% of the observing time and will be simultaneously optimized for the homogeneity of depth and the number of visits and for time domain science. Okay, so it will find it is a synoptic survey, which means it wants to measure the universe as it changes over short time scales. So it will be very useful for the discovery of moving objects as well. So it is expected to discover very large number of asteroids, maybe comets as well. It will discover large number of supernovae. It will aid in our study of variable stars and so on. And the good thing from the study of galaxies is that it will provide the deepest images ever taken of large areas of the sky, about half the sky. What we have right now is the Sloan Digital Sky Survey. This will be 5 magnitudes or approximately 100 times deeper than what the SDSS produces has given us. And therefore, we will be able to do science that we cannot even envision at the present time. So many ideas about galaxies can be explored with this. And needless to say, many people in the world were interested to join this project. And 2 years ago, we had an opportunity to do that. They invited international collaborators to join, and people who could suggest projects and could suggest contributions that they themselves will make that will drive the project were invited from the international community. They got thousands of applications, and they've selected a few hundred, several hundred projects from, I think, about 30, 40 countries of the world. And from India, there have been about 15 projects that were proposed and were successful. So in IUCAA and in NCRA and in several other institutes in India, we now have a few people, a few PIs who are part of the international data rights holders list. So we will have access to the data. I'm one of them, and there are several people in IUCAA as well. The remaining 10% time, in IUCAA, there is Surhud, there is Kanak, there is Shomak, there is Anuprita, there is Sukant. I think these are the 5 people at IUCAA. And there are about 10 other people across the country. Surhud is the main driver, the program manager for this. The remaining observing time, the 10% time, will be used to obtain improved coverage of the parameter space. So they will do very deep observations. Pencil beam observations of various deep fields will also be done. There will also be some observations which will be done with very short revisit times, so that things that change on time scales of hours, etc., can also be studied well. And observations of special regions, the ecliptic, the large and small Magellanic clouds, etc., will also form an important part of the study. The ecliptic, because one of the mandates of LSST is to find near-Earth asteroids, and these are typically in and around the ecliptic region, and therefore they'll find very, very small asteroids also. Okay, right. So now back to lensing. So the first lens was discovered only in 1979, about 40 years ago. So this is an image of a quadruply lensed quasar. So this is the lens, it's a galaxy, and the background quasar image is 1, 2, 3, and 4. Okay. This is from a more recent image by Falco et al. But the question is, why was the lens not discovered sooner? Couldn't they have discovered it in 1960? Sensitivity, or is sensitivity a problem? Correct. So can you see the scale here? The scale here is 1 arcsecond. So very, very small. So until your resolution improves to the level where within one, it is much better than 1 arcsecond. 1 arcsecond is the typical seeing that you get in this kind of telescopes. Not this particular image, but this one was done with adaptive optics. So the best way that we have now to do it is to do wavefront correction of the incoming thing, or go to the Hubble, and I'll show you examples of lenses discovered with Hubble. So now, yeah. Yes, but it won't do strong lensing. It will do mostly weak lensing. Okay, and for weak lensing, it can be done with the ground. You don't need adaptive optics, or the near reason it does not have adaptive optics, LSST, because you have to do it over a very wide field of view. It's not possible now. Right. So that was the reason it was not discovered sooner, because until you had, this is of course is a fantastic image made with, I don't know whether this is HST or adaptive optics, I have to check, but both are possible, because by that time BLT had also started working. This is an example of galaxy lensing. So what you see, this is with the Hubble Space Telescope, and these are Einstein rings of galaxies, typically blue galaxies in the background, okay, lensed by a massive galaxy in the foreground. This is the lens, and this is the lens. The arcs are formed by lensed objects. And there was a very large project called SLACS with the Hubble Space Telescope. SLACS stands for Strong Lensing with ACS, Advanced Camera for Surveys, one of the instruments on the HST. And they found many lenses like this, galaxy lens. Okay. But you can also have gravitational lensing by a cluster. Okay, so suppose you have, let's say, a blue galaxy in the background, line of sight. Every ray of light gets bent, and some of them reach us here on the Earth. Okay, and the amount of lensing naturally depends. Now, this lensing is happening by the cluster as a whole. So the whole cluster is acting like a lens. So it depends on the not the amount of bending depends on the mass distribution of matter along this direction, right? And so in this case, you can see lots and lots of arcs. Okay, so this is your most of the galaxies here are part of that lensing cluster. And the arcs that you see here, you see some arcs here, you see an arc here, you even see an arc here, you see some arcs here, and so on. So you can have 10, 15, 20 arclets that are there in the image. This kind of work can only be done with HST because you need that kind of resolution in order to make sure that that arc is not washed out. If you take an image with a regular ground-based telescope of this cluster, you will find that the arcs are all washed out. Yes, I'm going to come to that. So a single arc can form multiple images, but you can also have multiple galaxies getting lensed by one cluster. Okay, so the main characteristics of lensing, of course, it's sensitive to all matter, dark matter plus baryonic matter. Doesn't matter what form the baryonic matter is in, it will get lensed. The important thing to remember is that in the GR equations, the bending of light is wavelength independent. So that bending angle alpha does not have a wavelength dependence to it. Okay, and therefore it can be in principle observed in the optical and in the radio or other bands as well. And what you can do is, once you have, let's say, a cluster lens and you have all these arclets, you can build a lens model. Okay, so what you do is you basically take a cross section, and what will happen is that you can make, like in optics, we make this thin lens assumption, right? Similarly, you can make a thin lens assumption for the cluster because the thickness of the cluster is very small compared to the distance between us and the cluster and the distance between cluster and the lens source. Okay, so because of under those assumptions, you can then build a mass model. So unlike a simple point source lens, this mass model need not be uniform. There'll be galaxies, there'll be maybe there's some more dark matter in one part and less dark matter in other. So the distribution is not going to be totally uniform. So you can actually construct, so these contours indicate the sort of surface densities of matter, all matter in this case. And you can iteratively construct a mass model that explains each and every arc that you see. Right? And it should also explain, I mean, color can be a important distinguishing feature of the arc. So for example, if you see one blue arc and one yellow arc, right? Because the bending is wavelength doesn't change the wavelength. Okay, this blue galaxy and that yellow galaxy, both are distorted. They can't be the same object. They will be different objects. So all of that has to be explained. So you will have to build a mass model that self-consistently explains all the arcs that you see. And more the number of arcs, the more constrained or the better constrained is your mass model. Right? You can't do it with 1 or 2 arcs, but if you have 10 arcs, 15 arcs, then you can do it. And so this has been done for some able clusters. And then now the mass distribution, you can also cross-check it with the virial theorem. Okay, you get the virial theorem. If you build this, gives you a mass distribution, unlike the virial theorem, which gives you the total integrated mass of the cluster. You build your mass model, you integrate it and find out what is the total mass of the cluster, dynamical mass, and see whether it is consistent with the velocity measurements of the cluster, of galaxies in the cluster, and see whether you get a consistent answer. You can even do this while you are building the mass model. So as you iteratively build the mass model, you continuously check whether your mass model, the total mass obtained with your mass model, is consistent with the virial mass, and so on. So there have been for a few clusters. Obviously, this is very complicated stuff. There are many things that can go wrong, but it has been done for a few galaxy clusters using data from the Hubble Space Telescope. When you can build galaxy mass models, you can do something very, very interesting. So this is an image of something known as the bullet cluster. So there is an image with the Hubble Space Telescope in the background, okay, multi-filter image. What is shown in red is the X-ray emitting gas. Okay, so what has happened here is that there are 2 clusters. One is this cluster, and then there is this smaller cluster over here. This smaller cluster has actually passed through like a bullet through this cluster. And this gas is the displaced gas from this cluster. And this gas is the displaced gas from this cluster. Yeah. Very, very fascinating. And what does the blue color correspond to? The blue color corresponds to the mass model of the cluster that was built using gravitational lensing. So now this is supposed to be one of the strongest evidences against dark matter being does not exist as distinct particles, but there is some modified Newtonian dynamics, right? Why is that? Because in all models of modified Newtonian dynamics, the center of mass of the dark matter and the center of mass of the baryonic matter is the same. You change only the laws of physics. In this case, the mass in the gas is very large, okay, larger sometimes than the mass in the galaxies. So the center of mass of this particular cluster of the total mass is somewhere here. But the center of mass of the baryons is shifted to the right. Similarly here, the center of mass of the total matter is here, and the center of mass of the baryonic matter is shifted to the right. And of course, baryonic matter, we know that interacts differently. It interacts with other baryonic matter as well. So when the clusters went through, the dark matter was not affected, but the baryonic matter, particularly the gas, which collided and formed these kind of shock waves, shifted the baryonic center of mass. And the shock wave that you see here is this one. Suppose you have a bullet passing through some medium, dense medium. It produces a shock. It produces a shock front like this. And this is the exact shock front that you see over here. So very interesting observation that combines optical observations, X-ray data, gravitational lensing, and building of mass models of these two clusters. Okay, so now strong lensing is where you see arcs. Weak lensing is where you don't see any kind of lensed, separate lensed images or arcs. It's something that is statistical in nature. Here we look for distortions in shape that affect the average shape of galaxies. Okay, and here anything along the line of sight can affect the shape. So what I said a bit earlier is that it may be deflected multiple times on its way to us. These will all be very small deflections in the direction. But what we will see, the net deflection that we see will be a function of all the matter that it has encountered in its passage. It is very useful to probe the large scale structure of galaxies on very large scales, 0.1 to 10 gigaparsecs. So very large scale. So why is it statistical? Suppose you have all perfectly spherical or circular galaxies. Okay, and let's say you have a lens in front. Okay, what that lens will do is that it will distort the shapes of all galaxies. Now, if you knew for a fact that all these galaxies are spherical, then your job of building the lens model becomes very easy, right? Because all you have to do is work out the specifics of this lens, which will take this and transform it into this observed distorted image. Okay, but in practice, the job is much harder because not all galaxies are spherical. Their galaxies, some are elliptical, some are highly elliptical, and so on. So what you're going to start with is a population of galaxies like this with different ellipticities. And then you are going to lens it and get distorted images of each of these galaxies. So now you have to use very complicated statistical techniques to try and disentangle what part of the galaxy's observed ellipticity is due to its inherent ellipticity and how much of it is an additional shear that is imposed by the weak gravitational lensing. Okay, but the advantage here is that you don't have to do it with one lens and one lensed object, right? When you observe many galaxies which act as lenses, and you observe many galaxies which are lensed. So here they've in this picture, imagine that these blue galaxies are all distant galaxies at some large distance, and this is what is shown in red or orange is the cosmic web. And as that galaxy light comes along the cosmic web, it is going to get distorted, and so the image that you will see for every galaxy will be slightly distorted. So by including all the galaxies, all these galaxies which are lensed, you can construct a mass model of the matter distribution in this direction. Okay, does weak lensing really work? Okay, and again here for clusters, for some clusters you can build weak lensing models. So this is an example of a cluster where there's no strong lensing, no arcs were seen, only weak lensing was there. And this is the mass model, weak lensing mass model for this cluster. This is the weak lensing model for this cluster. And what you see here is the X-ray emission. So again, this is a pair of colliding clusters. The collision has pulled out the gas, the baryonic hot X-ray emitting gas out of these two clusters, and gradually will fall back. But the weak lensing model allows you to do this. Right? You can also do it over somewhat larger areas, not for a cluster, but you do it for a survey. And it was done for a fairly large survey done with the HST called Cosmos. And so what they did was they basically observed a certain patch of the sky. And this is your redshift direction. They measured the shapes of many, many galaxies, which were embedded in this cosmic web. And then they constructed mass models at every redshift. Yeah. The gas that gets heated, etc., is all lying outside. It's in the intra-cluster medium. It is not something that is pulled out of the galaxies themselves. So the galaxies, unless they come very close to each other, they may not get affected. They may just have gone through. But if you're right, if they come close together, it may affect star formation. Yes. Right. So in this Cosmos survey, what they've done is using tens of thousands of galaxies, they've constructed a mass model of the universe. And now you can compare this with real dark matter simulations, see the power spectrum that you observe from these from this matter distribution, and compare it with what you expect with various models of various cosmological models, and you will get a good match. Huh? Sorry? No, this is like a pencil beam survey, very narrow but very long. Okay, so this axis is quite long, and therefore you can see a very inhomogeneous. No, I mean it's long but not that long. Okay, so it's long compared to this extent. So you can't go very, very deep because of this. And you can't say that this is homogeneous. I mean, this is the total matter distribution, which is averaged over small chunks. So that's why it looks inhomogeneous, right? But it may be, if you average the density over this entire box, it may be like everywhere else. Okay. You can do weak lensing for cosmology, okay, but you have to be very careful about the systematics, about the measurement of the point spread function. So the point spread function, remember, also changes the shape of galaxies. So if you're seeing a small distortion in galaxy shapes, like a 1% distortion. If you're seeing a 1% distortion in the galaxy shape, is it because there is a real distortion in the shape, or you have measured the point spread function incorrectly in a systematic way? So you may be seeing a shear, but that shear is just your PSF is wrong. That's why you're seeing a shear. So it's very, very important to handle the systematics correctly. But if you do that, you can do what is called 3D lensing. So that is tomography. It's like a CT scan. You take galaxies at one redshift. They will be lensed on. They will be lensed only by stuff that is in front of them, not by stuff behind. Then you take the next redshift slice, and so if you have a large pencil beam survey where you measured the redshifts for thousands of galaxies, you can do this kind of mass modeling in different slices in redshift, like we did for the cluster. And that was how that 3D tomographic map of the Cosmos survey was constructed. Diffuse radiation, like the CMB, can also be lensed by the foreground. So the acoustic peaks, etc., that you have in the CMB are affected by the lensing by the foreground also. So the CMB photons are getting lens. So when you build a CMB map with the foreground subtracted, you don't just account for the fact that foreground emission is there. Like from our galaxy, there is infrared emission, which you have to model and take out. You also have to account for the fact that some amount of lensing of the CMB has happened, and how you can deconvolve that in your measurement. We don't get a lot of, we do get a lot of lensing, but remember the probability of bending in one direction and another direction is the same. Okay, so you don't have an expectation value of the lens deviation to be very large. So it's there, but it's going to smooth things out. So if you have let's say an acoustic signal on very small scales, an acoustic peak on very small angular scales, because the light is not coming straight, but it's bending many times along its line, along its path, you are going to see that signal getting smoothed out. So that they have techniques to correct for. Lensing has so far been done mostly in optical, mainly because only in the optical, at least for strong lensing, and even for weak lensing, do you have sufficient number of shape measurements at different redshifts to do the mass modeling. In the radio, we will be able to do something like this, but not before the square kilometer array. With the SKA, we can do what we are doing in the optical, in the radio bands. And as I said, the deviation angles are similar. You don't have to worry about it. Okay. So I will now introduce the next topic we are going to cover, which is called stellar population synthesis. Okay. So now we said that starlight that comes from galaxies, even if you have 10 raised to 11 stars, stars are very small compared to the distances between stars. So you can, to a first approximation, just add up the light from individual stars to get the total light of the galaxy. So the question is, how does starlight from 10 raised to 11 stars add up to form galaxy light? That is, if you want to construct a galaxy spectrum by summing up the spectra of the stars, what are the things that you need to know? Yes, so at that given instance, but so as of today, what if you want to model my Milky Way, 10 raised to 11 stars are there. How many M-type stars are there? How many K-type stars are there, etc. You need to. But can you construct that using some other quantity? Using the initial mass function, correct? You need to know the initial mass function, but you also need to know age, which means you need to know when each star formed. So what is the star formation history of the galaxy, right? So you need to know what is the star formation rate as a function of time, not just now, but over the entire lifetime of the galaxy. You need to know the star formation rate, correct? So that's fine. So we need to know the star formation history. We need to know the initial mass function. What else? Shape. Shape is not important because the type will influence the star formation history. So for example, if it's a spiral, it will have good amount of recent star formation. If it's elliptical, it won't have recent star formation. What else? Correct. So you will need measurements of the rotation curve in order to disentangle, take out the Doppler velocities, etc. But gas content, how will that affect the spectrum? Sorry? Extinction. What is more effective than gas in extincting? Dust. Okay, so you will need to know the dust distribution. Okay, but dust will dust change the spectral lines in the spectrum? No. Okay, it will change the continuum shape because it will attenuate some wavelengths more than others. So yes, so the amount of dust that is there is also important. So let's see if we have captured all of them. So first of all, IMF, we need to know the IMF. We also need to know stellar evolution, which means how do stars evolve in time on the main sequence and outside it. So you need the whole stellar history, not enough to know that, okay, so many stars formed today and so many stars formed 100 million years ago. You need to know once a star forms, how much, as a function of mass, how much time does it spend on the main sequence and how much time does it spend outside of it. Okay? Because their color, luminosity, spectrum, everything varies. The Earth, the sun, when it's on the main sequence, is a G-type dwarf. But when it becomes a red giant, it will have different luminosity, different spectrum, etc. Right? So we need to know that. What else? How will that affect things? That will affect the star formation history. So if I give you the star formation history, you have already captured that. Right. But there's one more important thing. Okay, you need to know you have a spectral library as a function of metallicity that tells you what is the spectrum. So if I ask you, okay, I have one G2 type star here, it has a metallicity of 0.5 solar, it is so many years old, can you tell me the spectrum that this star will have? So you need the spectrum as a function of age, as a function of mass, and as a function of metallicities. Okay. So this library can be built up in two ways. One is empirically. You just go around, find a star which is a G-type star and of this particular main sequence and this metallicity, and make a measurement of its spectrum. Just observe the spectrum directly. That is one. Or you can do it synthetically, okay, which means you have some stellar structure and evolution model, and based on that model, you just plug into the model what spectrum you want and it will give it to you. Both of these things are being done and have been done. So we have this. But it turns out that all of these are very uncertain at high masses and low metallicity. Why is that? High mass and low metallicity. They're evolving fast, that's one, but more because you are anyway doing it at a given instant. Okay. Today, what's the star formation? Do you think there are examples in the nearby universe of such kind of objects? High mass, low metallicity stars. Could you find some in the Milky Way? None. They're actually zero high mass, low metallicity stars in the Milky Way. Because we know that we are currently forming stars only in the disk. And the disk is very metal rich. Only second generation stars are. So The high mass stars will be high metallicity. There can be a low mass, low metallicity star that you'll find in the halo, for example, in the stellar halo. There's no problem with finding those. But finding high mass and low metallicity stars is very difficult. And because of that, both the observation based thing you cannot do, right? You don't find any single example of a star which is in that thing. But more importantly, you can't even constrain the models. So the models will give you some answer, but whether that spectrum that the model is throwing out for a high mass, low metallicity star, you have, since you cannot validate it with the real observation, you have no idea whether it's correct or wrong. So because of this, but let's say, fine, we will worry about this later. Then of course you need to know the star formation history. When did stars form and at what rate? And then you need to know the distribution of the dust. The gas attenuates very little. Over the entire, for high redshift galaxies, the gas-based attenuation is significant. But for low redshift objects, that is very small. And hydrogen gas is transparent. But dust is a very strong attenuator, but it's particularly strong where it's present in large amounts, like in spiral galaxies. And that needs to be modeled, but that is relatively easy because if you have a dust model, so which means the dust model will just tell you that given some optical depth, what is the amount of attenuation you will see at a particular wavelength. And there is, as always, a power law dependence of that, and you can model the dust. After that, it is just arithmetic to get the galaxy spectrum. And if you know the star formation history over the entire lifetime of the galaxy, you can construct the evolution of the entire galaxy spectrum also. So you can say that, okay, Milky Way today is today the situation is like this, but since I know the star formation history, I'll go back 5 gigayears and I'll predict the spectrum of the Milky Way 5 gigayears ago, and you'll be able to do it. Provided, of course, the degeneracies in this are small. Provided they're small, the more data you have, it will be small. Yeah. Yeah, you can predict this future evolution, but that's harder because the star formation history will get affected by things like mergers and so on. So the Andromeda merger is going to change the star formation history drastically. You know the star formation history when you have the spectrum. So for example, in elliptical galaxies, we say that elliptical galaxies don't contain any young stars, they only contain old stars. How do we know that? Because if we take the spectrum of any elliptical galaxy, you will find invariably it looks like 10⁻11 low mass stars. Even if they had 10⁻4 high mass stars, the spectrum would have looked different. So from this total integrated spectrum, we can rule out the possibility of having even a few high mass stars. So from the spectrum is essentially how we can tell that this is. Correct. Until JWST. Yes. So we can't measure, but now with JWST, near spec, we will be able to measure the spectra of galaxies, not of individual stars, because we believe that in the high redshift universe, the IMF was very top heavy. So very many high mass stars form. And in any case, they dominate the luminosity. So we will be with JWST not be able to get the spectra of individual stars. We might be able to detect individual stars at very high redshifts, but we will definitely be able to get very good quality res frame optical spectra of galaxies that are highly star forming with a top heavy IMF in the distant universe. By distant, I mean at redshift 3, 4, 5, etc. And we'll be able to get the metallicities. We'll be able to get the spectrum of low metallicity stars, which we will be able to compare with our models. Yes, but that is okay. It doesn't affect the recent universe, right? In the recent universe, if you take a Milky Way like galaxy, suppose there were a lot of, as you said, the low metallicity objects are all at high redshift. So if, let's say, initially it formed a lot of low metallicity stars, those are long gone. So they don't contribute to the light budget now. So it's not so bad. Are there any questions on the Zoom? Yeah. So we will then stop here and